and we are online.
Hello.
Hello, everyone.
Ciao, Maura.
So,
Luca.
hi. Please, Antonio, mute yourself. So we start. Okay. Hello, everyone. I am Maura Pintor. I'm a postdoc at University of Cagliari, and I'm a co-organizer of this event on machine learning security. Today, we are hosting Konrad Rieck. But right before we start, I would like to share with you some information on the seminar. So first of all, the seminar is live streamed and recorded. So if you don't want to be recorded, just leave the Zoom call and follow us on YouTube, where we also live stream. If you want to ask questions, you can do it during the talk when Konrad pauses for a specific question time, or when at the end of the talk by raising your hand on Zoom, or writing in the chat on Zoom, or also writing in the chat on YouTube. The priority will be first the raised hands, then Zoom chat, and then finally, eventually, YouTube questions. Then, if you want to be notified about a new event that we have, follow us on Twitter, LinkedIn, or also on the website that I will share later in the chats, so you have the links. And lastly, well, we also have a course on machine learning security on our YouTube channel. So if you feel like you want to know more about machine learning security, feel free to check it out. It's free and it's available in our channel. And lastly, let me thank all people who helped me organize these seminars. And now I'll give the stage to Luca, who will present the speaker.
So, Konrad Rieck is a professor at TU Braunschweig, and he also leads the Institute of System Security. Previously, he worked at the University of Göttingen in TU Berlin and Fraunhofer first. His research focus is the intersection of machine learning and computer security. With this group, he develops intelligent methods for detecting attacks, analyzing malicious code, and discovering security vulnerabilities. He received the CAST GI Doctoral Award, a Google Faculty Research Award, and recently an ERC Consolidator Grant. And congratulations for all of these things. So I leave the stage to you. Thank you again for being here, and everybody enjoy the talk.
Yeah, so thanks a lot for the invitation, and thanks a lot for these nice words. So can you see the screen now? Yes or no? Can somebody?
Yes, we can.
Yes. Okay. So then I will start. Yeah. So I first of all, I like to thank again for the invitation. So I think this is one of the very few things in the pandemic that makes the scientific life a little bit more interesting. This is that we can have more video seminars, and instead of traveling all around the world, which is also nice, by the way, but we can at least listen to many people from different countries, and I think this is great. And that's why I'm here, and I like to talk about a recent thing, and this is image scaling attacks. And I chose the topic because it is very visual, so you can see something. And I think for a talk, this is better than something boring, where you cannot see something. Yeah, let's just start. Wait, is my, wait. Yeah, so let's just start with what this whole seminar is mainly about, which is actually attacking machine learning, or sometimes adversarial machine learning. So this is where most of the papers and a lot of research has been published in the last years. And it's over thousands of papers that focus on this very topic. And you can see here on this picture a typical machine learning pipeline workflow. On the top, the training, on the bottom, the application. And then you hopefully can see these needles. And each of these needles is some attack that destroys some wonderful learning algorithm or another adversarial example that hits somewhere into the wonderful machine learning pipeline. And if you look very carefully, you can also see small dots. So there's more, you can put more needles in, so there are more holes for your attacks. And this will likely go on for several years. And yeah, so, but the truth is, and this is what my talk is about, that a real system doesn't look like this, but instead there is something in front of the learning algorithm. And this is extremely boring. It's preprocessing. Preprocessing is what your students or what you have to do, but you don't want to because it's so boring. You have to normalize the data. Maybe you need to extract features. Maybe you need to parse something. And in computer vision, you typically have to scale the images. And when I was when I was first confronted, I also thought that this is really boring. Why should somebody look at image scaling? How my PhD students, however, could convince me that this is not so boring at all. And this is essentially what this talk somehow revolves around. And it's structured in 3 parts. So we will first break image scaling, then we will understand image scaling, and then we will fix image scaling. So it's not like the other typical talks that in adversarial machine learning that just break something and then they say, yeah, it's broken. Instead, I will go through the typical stages that you maybe would do in software engineering. You find something, you try to understand what's wrong, and then you fix it. So this is for you maybe then a positive takeaway message. In the end, we are all very happy and secure. I have to say that, of course, this is not my sole work, but instead this is the result of teamwork. And most importantly, it's the work from Erwin, who's here. He's the first author on our paper and also on some follow-up papers. I think he's like the mastermind, and I'm more the messenger here. So I transport this wonderful research from my group to you. Okay, so that's another thing. Before I start, the whole topic has a little bit of an internal story. So I'm also telling the story, which makes maybe the talk a little bit more interesting than just going to the pure facts. And the story starts way back in 2019. There was a paper at USNIC Security Symposium, and this was from Chinese authors, and they essentially proposed something that they called image scaling attacks. And when I read the paper for the first time, I saw this formula that you can see here in the middle of the screen, and it looked like a typical adversarial example optimization problem. I'm not sure if you have seen something like this, but all of these attacks where you make a neural network misclassify something, all of these attacks typically build on an optimization problem. And this looks almost the same. And I thought, oh man, this is boring. Yet another adversarial example paper. So let's look at the formula. Can you see my mouse? Yes, okay.
Yes.
So what we see here is a perturbation. This is a little bit of noise. And the attacker wants to generate this noise on a very small level. So he's using this minimization to make small noise for his or her attack. And then this perturbation is added to an image S. And then the whole thing is scaled down to some smaller version. And then it's somehow compared to something that is T. T is our target. And the whole thing should be smaller than epsilon. So this means we are optimizing this noise such that the result, when scaled, looks like T. I must say, when I first saw it, I was not really impressed. And I was on the, I was kind of, don't look at this. This is just one of 100 different adversarial example papers. But Erwin, my student, he did something very smart. So if the professor refuses to look at a topic, you need to convince him. And the best thing to convince him is with an example. So what he did is he prepared an example. And I show this to you. So on the left, you can see a cat. And on the image, there's a small level of noise that is very difficult to see, if at all. And if this image is scaled, it completely changes and becomes this dog on the right. And there's no further trick or change. This is just the scaling operation by magic changes the cat into the dog. And if you look very, very carefully into the cat image and you magnify the regions, then you can see this noise. In contrast to adversarial examples, this noise can be seen, but you have to look very, very carefully. And maybe you can see it on your screen here in this magnified region. There are these small dark dots, and these are essentially the attack pixels. So when I saw this, I said, okay, let's do it myself. So this is what I can also do this because it's just a Python script. And I can almost run Python scripts myself. It's only a little help. And so what you can see is, again, a city. And if the image is scaled, the city changes completely. It's a different part of a city. Here you can even see the noise a little bit better because in the sky, there's some kind of very fine grid pattern. But I would argue that as a human, you would never expect this grid pattern to have such a strong effect on the scaling. So when I saw this, we started to think about what's happening here. And the first thing that we did is to think, does this matter? Could this be a problem? And the first thing that we noticed is that the threat model here is different from adversarial examples. So we are in a new setting. The setting is that whatever we do, it does not depend on the learning algorithm anymore. So these needles in the learning algorithm, they don't matter because we can change the image completely. And therefore, whatever happens after this transformation doesn't matter. It's under our control. So the attacker at this point has 100% control. And what the attacker needs to know is what scaling algorithm is used and what the size of the scaling is, the output size. Most of these informations are typically no secret. If you download a machine learning model, very often the scaling is in the first lines of the code and it says, okay, scale the image to this dimension and then do all the other stuff. So you can do some very interesting attacks. So let's look at two. The first is a poisoning attack. Here I prepared two images. This is on the left. So you see the street sign, it says 40. But if it is scaled, it becomes a 10. And this means that the learning algorithm trained to recognize a sign of 40 will actually learn that it looks like a 10. So your car will drive faster when the car sees the street sign 10. So that's a dangerous attack. And if you look very carefully, you can even see the attack in the 4, right? There is this, it's a little bit in the background, but yeah, it's not completely invisible. And this would be something that you do at the training stage. So when your machine learning model is trained. And on the right, you can see an evasion attack. So this is something that you could do at the application or inference phase of machine learning. That's a photo of me. It has this typical, I'm not sure if this is all the same in Europe, but in Germany, you have to look very straight into the camera and there's this kind of biometric. And so everybody looks a little bit more ugly than usual. So this is the original photo from my passport. However, if it gets scaled down to a particular size, it changes to James Bond. And this would mean that if for some reason Interpol or the FBI is hunting for me and they use this information from my passport, they would look for a different face, which would be very good. So I hope I can convince you that attacking the scaling before all the machine learning stuff is an interesting, relevant setting, and that it can be used for different types of attacks. So the next question, of course, is, yeah, okay, but where does this happen? Is this something that is present in all scaling algorithms, or is it just present in one scaling algorithm, and things like that? So we looked at the three major machine learning frameworks, TensorFlow, PyTorch, and Caffe. And we looked at the scaling algorithms and we tried this optimization problem for the different scaling algorithms and checked, are they vulnerable or not? And if there's a red check mark, this means yes, they are vulnerable. And if you see a green cross, they are not vulnerable. So what's the message? The message is all of them have one vulnerable implementation. TensorFlow has 3, Caffe has 4, PyTorch has only 1. So it's not super clear what's going on. But unfortunately, the default algorithm typically is vulnerable. So that means that if you don't care and just apply scale or something, there's a chance that you run into this problem. Now you see the versions here. So some of those frameworks have changed after our publication. I'm not sure if this is a result of our work or more or less that they were also very curious about what image scaling is. But if you use these versions, they are in fact still vulnerable. And essentially, this kind of concludes the break it part. Now it's broken. And if you have questions, we can talk about them now. If you don't have questions, we can also proceed. So maybe I'm just waiting for questions.
Actually, I have a quick question. Would this attack work also if you print the image?
No, I'm.
Or maybe it's something you didn't test. So
it's something we did not. So the problem is, we will see this in the next part. It really depends on the particular pixels. So the attack, like adversarial examples in the classic fashion, works at the exact pixel positions. So if you print something and then take a photo and you align it perfectly like the original, then it works again. But if you move it a little bit to the left or right or top or down, it does not work anymore. And I think this is also in contrast to there exists something like physical adversarial examples, something like these patches that you can put on your closes. This does not work, and you can even almost prove this will never work in a changing environment, because as we will see in the next part, it depends on very specific pixels and their role.
okay, thank you.
Okay, so no further questions, I guess. So then I will just move forward. Yeah, okay. So what we want, of course, at this point, we were very excited, but we also had to notice that the paper from 2019 already introduced the attacks. So we could not just resell them again, but we had to do something more. And we wanted to know what actually is going on here. And the original paper talked about machine learning and this being a very complex process, blah, blah, I would say, because the scaling algorithm is unrelated to machine learning. It's not a learning algorithm. It's just a very simple algorithm. So why not try to really understand what's going on? And this is exactly what we did. So we took the 3 implementations, and then each of the PhD students had some of the code from this implementation. It was implemented in C. And they went through the C implementation and checked precisely what are these algorithms doing, what's going on. Something that you cannot do, for example, for a neural network, because you have millions of neurons and millions of weights. Here we don't have the setting, we just have something. And the first thing that they noticed in all of the implementations, the scaling is not a 2-dimensional operation, as I would have expected, but all of the algorithms first scale horizontally and then vertically. So they kind of fit the image like this first and then like that, or the other way around. But what they don't do is they don't apply a 2-dimensional operation. So they don't move it in one step. And essentially this boils down to 2 for loops. One goes over the rows and one goes over the columns. And then you are done with the scaling. And this means for us, for our analysis, that whatever goes on happens in a 1-dimensional signal. So in a row, for example, from the image. We don't need to look at something 2D. We have a very simple, clear setting. There's a long row or column, and it's just pushed together. That's it. That's what scaling is doing. And this aggregation, this moving together, this builds in all of the algorithms on pre-computed weights. So there's a matrix somewhere inside. It's not a matrix. You see, I'm already making the mistake. It's not a matrix. It's just an array because it's 1-dimensional. And in this array, there are some weights. And then there's an algorithm, and that puts these things with the help of these weights together. Now, we looked further, and we noticed that this is something that we have seen before, more in the area of signal processing. And this looks like what is sometimes called a convolution. So you move over a signal, and then you apply a given set of weights and somehow aggregate or fold together the individual sample points of your signal. And depending on what these weights are, you use a different kernel function in this convolution. Don't confuse this, by the way, with a kernel function used in machine learning algorithms. This is typically a function that gets 2 inputs. Here you have a kernel function that only gets 1 input, and it defines a shape. And we can even look at these shapes. So here's what we essentially found out. The different algorithms, for example, nearest scaling, bilinear scaling, or bicubic scaling, they just have different kernel functions. And these kernel functions correspond to different weights. And these weights imply different shapes. So for example, nearest scaling means you put all of the weight at 1 pixel in the middle. Bilinear scaling means you have a linear function on both sides, and bicubic means you have these cubic functions. And as a result, when this algorithm walks over the signal, you assign different weights importance to the pixels of the image. Yeah, and where's the problem? So interestingly, we identified the problem, but when we talked to people from the signal processing domain, it turned out that this problem is actually trivial. So if you have a signal processing background, not sure if you have, but if you have, likely you already spotted the problem. So what's happening here is a signal is downsampled, so its frequency is reduced, and there's no low-pass filter in between. And if you do this, for example, with an audio signal, you would get some kind of noise in it, some kind of sound, because you have high frequencies that when this is folded together, these high frequencies result in some kind of spurious noise created during the sampling process. And signal processing people know this already for 100 years. Machine learning people know this maybe, and security machine learning people, of course, don't know this because they haven't taken all these lectures in the university, but spend more time on their computers, unfortunately. So what this signal processing theory says, you need to apply a low-pass filter on a signal, otherwise you get an aliasing effect. Sometimes you also see this when you scale an image yourself, that there are some kind of artifacts in the image. This is an aliasing artifact. And what is happening in the attack? It is essentially a malicious aliasing effect. So the attacker is using knowledge from this not present low-pass filter to create artifacts with control, so to say. And if you want to, we can even break it down in an even more simple message. And the message is super simple. It actually is most of the pixels during scaling are ignored. Yeah, so it's not what you would think that all of the pixels somehow play a role. No, a few pixels have a high weight, and many, many pixels have a very, very low weight due to the shape of the kernel function. I have an example to demonstrate this. So here we can see a one-dimensional signal on the left, and these bars correspond to the, let's say, to the brightness of the pixels. Yeah, for simplicity, I assume it's a black and white picture, and yeah, that's essentially the brightness. And now we are scaling this image from 1, 2, 3, 5, 9 pixels down to 2. And we use a bilinear kernel function. Then this bilinear kernel function would apply this kernel window to the pixels and then compute the scaled version. And the interesting point here is from all of these pixels, only 3 contribute to the final result. This one fully, and those 2 by half, to say. So this means what the attacker can do now, if he or she makes a modification here and there, he or she has full control over the output, and the rest changes not at all. And we digged a little bit further into this, and we could identify those factors in the algorithms that are responsible for this, for the amount of pixels that need to be changed. And there are 3 factors. So one factor is the scaling ratio. If this is a large image and you make it very small, this means more and more pixels are ignored. Then the shape of the kernel function plays a role. If it's very picky, it's clear that in the middle there's a high weight and the rest is. Whereas if it's more like this, there's more distribution. So you, as the attacker, you need to change more. And of course, the width of this kernel plays a role. Not only the shape, but also is it like this, or is it like that? Yeah? So is it like 10 pixels wide or 100 pixels wide? And we did a lot of experiments. This is all in the paper, so I'm not bore you with these. But I like to show one experiment, just as an example. And in this experiment, we investigated the influence of the scaling ratio on the attacks. I mean, we identified this as one of the root causes, so we empirically tested our finding. And what did we do? We selected 600 images, or no, image pairs. So 600 pairs. And the task was of the attacker to change one image from each pair to the other. And then we had a neural network, and the neural network was asked to classify the scaled image. Most neural networks, by the way, have a fixed input size, so scaling is kind of natural there. And we checked at what point the neural network would make a misclassification. And this happens, of course, you can always add noise to an image and at some point create some result. It's also something that sometimes is not precisely described in literature. So of course you can add information to an image such that it gets misclassified. The question is this noise visible or is it not visible? Because if I paint a dog over a cat, it's clear that the cat becomes a dog. So the question is it visible? And we did a user study to find this out. So we asked people, what's with this image? Do you see something special on it? And what you can see here now in the plots for TensorFlow is the result of the user study. If these bars are green, this means the people in the study said, something strange is going on with your image. There's some noise on it, or they said, it looks broken. Yeah? So the attack was visible. Whereas if the bar is red, this means that people did not see anything. And they said like, hey, this is a wonderful picture. Where's the problem? And it's clearly visible now that the scaling ratio plays a role here. And you can see, for example, that if the scaling ratio is 10, none of the attacks is visible from these 600 pairs. If you have a smaller ratio, like maybe 5 or 4, the attack does not work always, maybe 50% of the cases. But still, there is, I would say, a large fraction where the attack still works. And if you go down to a scaling ratio of 2, then the attack is, most of the cases, visible. So you see this noise. Okay, so we had these factors. I said we did this not only for scaling ratio, but also for the kernel function and the kernel width. And at this point, we were ready to fix the problem. So I can jump into this point where I say, I hope we understood now what's going on. And if you have questions, you can ask.
I don't see questions or raised hands, so I'm gonna
then
ask a question. So I would like to know if also you studied the performance of the machine learning model, varying the parameters of the, I mean, if it changes something, of course, probably you have to retrain the model every time for a different filter, I guess. I don't know.
No, since we control all of the pixels, the model is applied as is. So we take this image, the data comes from ImageNet. The model was trained on ImageNet, so it recognizes the different classes. And we do our attack, and we say the attack is successful if the neural network misclassifies the image as something that we want.
Sorry, yeah? I meant on standard images without attacking, just to see if changing the rescaling algorithm or parameters changes something in the accuracy of the model without the attack.
Yes, and we did this. Yeah, that's a question that we never had so far. Yeah, that's a very good question. So the scaling algorithms on clean data have a little influence on the model. And I find this very interesting. So it's not that, I mean, you would expect that if you change the scaling algorithm, nothing changes, the prediction remains the same. So there's a dog, it gets scaled down to a dog, it still looks like a dog. But these ImageNet classifiers, they have the tendency to confuse some classes because there are so many different classes. For example, there's like, I would say 10 classes of dogs. And every time I have to look up the names of these dogs when I work with this data. And if you change the scaling algorithms, so for example, you go from bilinear to bicubic, sometimes these near classes are confused, so to say. But there's never really a big error or so. It's just that the truth here is, I think, that deep learning is very fragile. So it's not so robust as people claim. And even small, minor changes can cause a slight misclassification. It's not the big misclassification, but it's that you have one dog race and another dog race, and they're just confused. So this is what we experienced. But in our case, we were doing targeted attacks. So we were really looking at going to a particular randomly chosen class. Okay, so then let's go to the last round, so to say. Let's fix this. And in principle, we know everything now. And I typically say what we want to have here is more democracy in image scaling. We want that every pixel somehow contributes to the decision, to the scaling, and that every pixel has the same weight. So we want a uniform weighting of the pixels, like in a real democracy. Yeah? So everybody has the same weight, no matter whether he or she is in the middle of the image or on the right, whether it's a green pixel or a blue pixel. Everybody is the same. Yeah, so essentially the democratic principle. And then we were like excited because we said, okay, let's invent a new scaling algorithm. Let's become famous because we designed a new scaling algorithm. And we designed it very simple. We said, okay, the kernel width, the size of this kernel window needs to be related to the scaling ratio. So if the scaling ratio is 2, we need to make sure that the kernel covers all pixels. And if it's 10, we need to make the window 10 times larger so that it covers all pixels. Yeah, so this is the first idea. And the second idea was we use a flat kernel function. So it's not picky, it doesn't have any shape, it's always like this. And then we were like already organizing the party for our famous scaling algorithm. And unfortunately, after a little bit of investigation, we found out this already exists. It is a known scaling algorithm. It's implemented in all of the frameworks, and it's called area scaling or area interpolation. However, it's always the last in the list. And the reason is that it is the slowest. So in all implementations, you find area scaling or area interpolation, but it's the last, and people often write that it creates blurry images. Could be that it creates blurry images, but from our analysis, we can say this should be secure. And we evaluated this again with these 600 image pairs. And in none of the 600 cases, the attack worked when we used area scaling. So here's an example. If nearest scaling is used, the original image is changed to a cat. The true image is a cup of espresso or so. And if area scaling is used, you can see the cup still clearly in the picture. Interestingly, the attack does not completely disappear, but if you look closely, you can see a little bit of the cat still in this image, but it's not enough to confuse the neural network. So VGG19, the model that we use, recognizes here a cup. There's no confusion with the cat. So we can conclude from this empirical result, but also from our analysis, that this defense protects from image scaling attacks. The advantage is that it's already there, so it's not difficult to use. The drawback is it creates these small artifacts if an attack is present, and the image is slightly blurry. So yeah, maybe, and this is good that we had the question in advance. So it could be that a neural network, for example, that is very picky, makes a slight misprediction because the image is not so crisp. So then we said, okay, if we cannot invent a new algorithm for scaling, maybe we need to invent something else. At least we wanted to invent something. And the idea was that if there's only a particular pixel in the image or a few of these pixels created by the attacker, what happens if we remove these pixels and reconstruct them with the rest of the image? In computer vision, this is a common task. So it's sometimes called inpainting also. So you have, let's say, an error on an image or something needs to be removed. And then later you use the rest of the image to reconstruct information that fits somehow. Of course, you lose information, but maybe your reconstruction is good. And in our case, we have only very few pixels and they are hardly visible by a human. So we were very optimistic that if we apply the attack, if we apply this reconstruction, the image looks okay. And technically, this is quite simple. What we do is we use the logic of the attack and identify here on right in red those pixels that the attacker needs to change. We know the scaling algorithm as defender, and we also know the scaling ratio, and we know the kernel width, and we know the kernel function. So we know everything. We can precisely say which pixels have an influence. And what we do now is we create a window around these pixels. And the window is, again, in relation to the scaling ratio. So it makes sure that every pixel contributes to the reconstruction. And the reconstruction happens that we replace the vulnerable pixel with something. And we designed two solutions. One is a median filter. So it takes the median of the window in color. So it goes through the three colors, and then for each color determines the median. It replaces the pixel with the median. And the other is my favorite reconstruction because it's so stupid. It's a random filter, which means you take the window and just randomly select one pixel from the window and put it there where the original attack was. I like it because it destroys the attack in a very simple way. So the attacker is now in a lost situation because his or her attack has been removed. And it's somehow funny that you do something random to protect in learning-based system that uses scaling. So let's look at examples. So again, on the left, we see the cat. So this is a working attack, no defense in place. On the right, you can see the median, middle, you can see the median filter. And on the right, you can see the random filter. And since we remove the attack pixels, what happens now is that the cat completely disappears from the image. There's no overlay on no small shadow. The attack is gone. The median filter looks excellent, I would say. The random filter, because it's random, has some kind of very funny random noise. So all these sharp edges now become very peaky because there's this random exchange of pixels. Still, the VGG19 learning model recognizes a cup here, and I think it's clear that this also looks like a cup, despite a little bit of randomization. So the bottom line here is we have two filters in place. These filters can be applied before any scaling. So this means you can still use your favorite scaling algorithm. You don't need to use area scaling. And the drawback is that the median filter takes some time because you need to compute the median for each window. Maybe you know there are some tricks to make median computation efficient. Yeah. But still, it requires you to go through all the pixels. And this is it's obvious here that it takes a little bit of time. The random filter is super fast, but it creates this random noise. So we say that if you have a very efficient, you require a very efficient application, and you can live with a little bit of noise, the random filter is your choice. If you have a high precision application and you have time, the median filter is your choice. If you want to have efficiency and high precision, then you're lost because also the area scaling is slow. So this is kind of the only drawback of the whole work. So here's an example of the reconstruction so that you can maybe see a little bit better what's going on. The left shows the attack, hardly visible if it's not magnified, and the right shows the cleaned image, and I would say I actually don't notice any difference between the two images, except for that if I zoom in, this grid disappeared. So it's really a nice defense. Of course, at this point, you typically should not stop in adversarial machine learning. You need to attack yourself, because otherwise, Nicola Scalini will do this anyway, and then destroy your work. So it's mandatory that you attack yourself. So we did this. And what we did is we integrated our defenses into the optimization problem. So maybe you remember in the beginning, I was showing this optimization problem. There was a scale function. And what we did now is we put our own defense or area scaling into the optimization problem and then just repeated the process. And it turns out, fortunately, the attack then fails. And it's not that Nicola Scalini can simply go and attack us right away. And we even did a little bit of proofs here, so it's not that this is just an empirical result. And the reason for this, the robustness of the defense, is that for each of the three defenses, we can make an argument on what the attacker needs to do to evade the defense. For the area scaling, we have a window, and the algorithm essentially takes the average pixel color. So an attacker that wants to control this average needs to change a certain amount of the window. And typically, you can estimate this needs to be on average 50%. Otherwise, the attacker cannot control the average. Similarly, we can argue for the median. If you want to select the median as an attacker, you have to control 50% on average of the pixels. And this means controlling that you need to make changes to them, bigger changes, and therefore the attack becomes visible. And the same holds for the random pixel. It's even better there. If you as an attacker want to control the color of a random pixel, you have to make all pixels the same color, because otherwise it doesn't work. And what happens now is that the attack still creates the perturbation, but the perturbation becomes so strong that it is super visible and also destroys the image. So here you could see this is, I think, a grasshopper and a dog, and the attack creates such a strong noise on the image that you can see both images, or maybe you can see nothing. Of course, I have to say this is our proof, and that we also have a little bit of mathematical proof in the paper, but I'm very sure that you can think about other ways of attacking this. And I would say so far, this is not broken, but maybe there are new ideas. There's one paper in circulation, I think it's on arXiv, that touches a slightly different setting, and voila, you can also break this. Yeah, if you want to know more, I can tell you how this works, but this is typically in security, and it's also great this way that people think, can they change the threat model a little bit? And is it still secure if I make this assumption or that assumption? So I think this is pretty cool. Good. Maybe I do the summary first, and then we have the final round of questions, because the summary is very short. So the summary is, I hope I could show you that image scaling attacks are an interesting and new threat, and they work in different scenarios. So that they are, I would say, they are interesting to study. And the good news is that we have found out that there exist defenses, some defenses like filters that we developed ourselves, but they are not very complicated. And also area scaling, which is existing and can be used right away. And we made our code for all of the experiments from the paper available under scalingattacks.net. So you can download it and you can do these same kind of attacks and play around with them. And the last point is maybe a more general, so this is kind of the bigger picture. This is why I find this interesting. So in the beginning, I showed this preprocessing. Now I looked only at image scaling, but maybe when you think about machine learning, you notice that there's many more preprocessing steps. And can we ensure that they are all secure? I would say no. And what we see here in our example is what I would call a disagreeing view on the same data. So you have data you apply an algorithm to the data from preprocessing, and then a human and a machine would see something different. And similar attacks exist already, but they are not kind of put into this framework that I showed to you. So for example, there's a recent paper on homoglyph attacks or Unicode attacks on text in machine learning. So in this case, they use strange Unicode characters to fool a machine learning system. And essentially, this is also the same story. The machine sees the Unicode characters that are strange. The human does not see them. So again, we have disagreeing views on the same data. Or take acoustic attacks that use what is called psychoacoustics. That's not only a strange word. This is the basic of MP3. So certain frequencies cannot be heard by humans. Not only high frequencies and very low frequencies, but also other frequencies in certain situations are not hearable, audible. And these attacks make use of this. So they add information into frequencies that humans cannot hear. But the machine, of course, can hear these information. And again, there's a disagreeing view on the audio, or it's not a view, it's a listening. So the human listens to something else as the machine. And we can even take this further and say, maybe it's not only human versus machine, maybe it's also machine versus machine. For example, in malware research, it's common practice that people add adversarial examples into some parts of a file that is not parsed correctly or that is parsed strangely. So sometimes the segments of files are not correctly parsed. And again, this would mean that the parser that executes the program sees the malicious file and executes it, but the parser used in the virus scanner does not see the malicious file. And again, we have the scenario, two disagreeing views on the same data. So I argue here that this is a family of problems, and we just need to look out and find more examples. Okay, that's it. And I'm looking forward for your questions. And I need to, yeah, go ahead, I'm listening.
So thank you. So first of all, thank you for the talk. It was very, very, very interesting. And I have a question and curiosity. So basically, I got triggered by the polyglot part because it was exactly what I was thinking while during the talk. Like, you have, like, you know, a file that is a PDF, and then inside the PDF maybe you have images and the work of Angelo Albertini, if you're familiar, that basically includes, so basically part of his research is how to include files inside files, like
yes.
And then putting the hashes of the file inside the file, these kind of things. So I was thinking this problem basically is connected to both the feature extraction phase and the before feature extraction phase, let's say. And I was thinking, if we change the domain, in general, say, like, let's say we have like a general domain, which is the first of the two that you should evaluate to understand if that domain might be vulnerable to a, let's say, scaling attack, where scaling is something in that domain, where you're projecting in a smaller space and you're discarding some of the information. It's more at the feature, like when you're engineering the feature, or is more like on the function that you use to process the feature? Because to me, they're kind of very, very related. Don't know if the question makes sense.
Yes, it makes sense. So the question is, the answer is like so. So typically the problem that you described, polyglots and so on and so forth, comes from the fact that parsing data can be quite challenging. And this is something that is known for, I don't know, 50 years. So parsing a TCP packet. I'm not sure if some of you have written a TCP parser. I'd once tried as a PhD student, and I failed because it has like 300 pages specification, and there's millions of corner cases. So writing a parser is super difficult. And this is one reason that you already have the problem before feature extraction. But now there comes this new world of end-to-end learning where people say, I don't care. I just throw a convolutional neural network on it or some LSTM, and it will pick up all the information. And in that case, of course, it's not visible anymore what's going on. But the question is, does the neural network also suffers from these problems with parsing? And I would say yes, because these parsing problems are rare. So for example, in TCP, when I did the parser, it worked 99.9% of the network packets, but it failed for every millionth packet because it was different. And I would expect a neural network to learn a very good parser, but not a perfect one. And the attacker, of course, can always look for this weak spot. And I like to add something. This is also a philosophical thing here that is known from intrusion detection for a long time. Ultimately, you could say the problem is solved if we wrote the perfect parser. This could be if you say, I perfectly implemented this. But this is not true. In intrusion detection, for example, you have a target system. Let's say this is a Windows system. And what you need to have as defender is the same implementation as the Windows system. So if the Windows parser of TCP is buggy, you as defender also need to have a buggy TCP implementation, because otherwise you might not see attacks that Windows sees. So we come to the point where we need to clone the victim. And by cloning the victim, we also inherit all the problems of the victim. So I think in the long run, it's a very difficult problem. That's not easy to solve at all.
Okay, thank you. The question was kind of vague. So, but thank you for the answer. Yeah. So we have another question from Catherine Gross. Catherine, if you want to unmute and show you, yes.
Hi, it's nice to meet you. So really nice talk. Thank you for this. I just have a question about a tiny detail. So you talked a little bit about the trade-off in terms of times when you apply the different defenses. But what I was wondering, if you consider the original downscaling and the mean and the median downscaling, does this make any difference in terms of visual quality?
So visual quality. So in terms of runtime, it makes a difference. Because most of the frameworks use nearest scaling, and nearest scaling is a little bit like the random filter. It just picks the pixel in the nearest to the kernel function, and therefore it's just a copy operation of pixels. In terms of quality, we didn't do any tests of quality, but at least visually, all of these images looked perfect. I could not see anything. I don't know. There might be, also the machine learning, the VGG19 model performed the same or close to the same, except for some dog and cat races, or I don't know, some of these there are some super strange classes in this data set. But in all of the other cases, I could not see something, but we didn't really measure this.
Okay, yeah, I was just curious about this. And maybe as a follow-up, so I would also be curious about hearing about this other threat model that has been introduced, but maybe we can see how many other people have a question, because I think this one would take a lot of time. But thank you so far.
Yeah, maybe it doesn't take so long of time.
Oh, okay, please go ahead.
The other paper, it's I know it's University of Wisconsin or so. I think what they say is that they say, okay, the attacker knows the machine learning model. So he knows the learning model and he knows the scaling algorithm. So he has two things. And now he wants to craft an adversarial example, but also wants to benefit that there's a scale in between. And the adversarial example becomes much stronger, I would say better now, because it's even less visible in the original image. And after scaling, it can kind of unfold its full power. So it's a super, I would say a super powerful attack. Now, unfortunately, the downside is that this attack loses this independence of the machine learning model. So it's now the attacker needs to know both systems and needs to attack both. And I think this is that's the weakness. So they changed the threat model. But yeah, I would say that our defense does not stop an adversarial example to go through this chain, because the adversarial example can be also in more pixels. It can be in 50% or even 100% of the pixels, and still is invisible. So it goes through. but at the same time, our defense does not protect against adversarial examples. So it's yeah. But I think it's cool work, and I hope it gets somewhere accepted. But as we all know, it's super hard for everybody to get something through.
Okay, thank you for the short summary. Really interesting.
So we have a question from the Zoom chat, which is, as far as I have understood, you have applied the median filter to all of the images before doing the prediction as a defense. Is there any way to differentiate between an attack image and a benign image?
Yeah, super cool question. Very good question. Yes, of course. This is, yeah, interestingly, there exist two approaches to defense here. One is destroying the attack, and the other is detecting the attack. And you are perfectly right. What we do cannot detect the attack. So you are safe, but you don't know whether you have been attacked. And I mean, there are scenarios where you want to know whether you have been attacked, and just instead of being safe. And there exist, I think, like 2 papers that do detection. And we are currently working on our own paper because we can break the others. It's always the same story. Break, understand, fix. So we do this again. So you, of course, if you have a detection mechanism, then you can try to break it by evading it. And then you can build a better detection algorithm and back and forth. But yes, this is that's a different task, so to say. And technically, just very shortly, how this works, just that you get an idea. It's good that nobody asked so far. So if you are familiar with computer vision, you know that many tasks in computer vision are not done in the original image domain, in the spatial domain, but they are done in the frequency domain. So you're not looking at the image as it is, but you're looking at the frequencies contained in the image. And the small grid that I showed to you, this leaves very clear peaks in the frequency domain of an image. And there exist different approaches that try to spot these peaks. Unfortunately, it's not so easy because images also can contain, for other reasons, frequency peaks. So because the background is noisy or has some kind of grid pattern and things like that. So it's a difficult task, but in the frequency domain, it's far more easier than looking at the spatial image domain.
Okay, so we have time for 2 more questions. Then we are gonna end the stream. And if people want to remain inside the Zoom, can keep asking questions. So Antonio wrote on the chat that he has a question, but he didn't text it. So please, Antonio, ask the question live now.
Thanks, Luca. Thanks, Konrad, for the nice presentation. I really appreciate it. I was wondering if you try to investigate if there exists some bound for your attack to work, a bound between the similarity of the source and the target image for the attack to succeed. So the question is, in another way, can I take any kind of pair of images for the attack to succeed or to work, or is there somehow a similarity constraint on between how I choose the two samples? Thanks.
Yeah, so I'm not. I think I'm not sure if this is the answer to your question, but we did randomly select the pairs. So all of the results correspond to random pairs. Now, the attacker does not need to use a random pair. He or she can search for the best possible target image that shows the class that he wants to have. And we found out that in some cases, there are images that already look very similar by accident, so to say. There's somebody with a green t-shirt and a blue hat, and there's an image of a house with green grass and a blue sky. So the colors are already very similar. And in that case, if the attacker now wants to find this match, the attack becomes more powerful and it becomes harder for our defense. And you can theoretically think of an example where the defense fails. And this is a setting where parts of the 2 images are identical. And there's only very small, let's say there's only 10% of the pixels that are actually different. And in this case, our defense has to fail because we cannot find these extremely small differences. So I hope this is the answer to your question, but random selection of pairs is what we did. This is kind of the average case. So an attacker that hunts through his database of 1 million images could potentially find a target that is better. But we assume that this is a very tedious task, but yes. Okay. Was this your question?
Yeah, you grasped the point. Thanks, Konrad. Thank you again.
So the time for the last question from the Zoom chat. But if you use your defense, isn't the newly proposed attack crafted for both scaling plus model very mitigated? As the scaling defense, such as the reconstruction, should weaken the adversary significantly? Question mark.
I'm not so sure if I understood the question. So what our defense is doing is it prevents the image from changing visually. Yeah. So if it's a cat in the beginning and it gets scaled down and we have the defense in place, we can be sure that it still looks like a cat, to a degree that it will still be detected by a neural network. However, if there's something invisible in the image, in the original image, it could be that also this invisible thing is transferred to the scaled version. And the reason that we cannot defend against this is that this invisible thing could cover the whole image. And therefore, even if we use all pixels for scaling and have a flat kernel, this invisible thing still is transported invisibly. And this is what this new attack is doing. I'm not sure if this was a question, but
no, actually, I think the question was referring to the to applying the scaling attack to obtain an adversarial image. So the basically the scaling plus adversarial attacks plus evasion.
Yeah, but this is what this other paper does. So it's kind of combining the two things, and the advantage is that you can create stronger adversarial examples. So for example, there's something called max confidence attacks or so, where you do not want to just cross the decision boundary, but you want to make the adversarial example high confidence. And sometimes this creates visible artifacts because you need to have stronger changes. But with the scaling attack on top, it becomes better.
And I'm not sure. What about with the scaling defense that you propose? Would it remove the adversarial perturbation as well?
If you apply it naively, of course, yes. But at this point, I would always look at the combination of the two. So I would not, if you apply a regular, I don't know, Kalini-Wagner attack and put scaling in between, it will break. But of course, you can crunch this together. Adaptive. Because it's also and somebody also said something very smart. And when I was presenting this in a vision group, they said maybe you can also calculate the gradient of the scaling. And we haven't thought about this, but it's likely possible. And then you can do an attack that takes the gradient of the scaling plus the gradient of the neural network and goes right through.
Okay, I think I'm gonna allow the question from Battista, even if we are out of time.
No, but okay, but feel free also to, if you have to stop the streaming, we can take this offline.
Okay, I'll stop the streaming, not screaming.
Then we scream after the question.
We scream later. No, thank you all for joining today and for listening to this interesting talk. And of course, thanks a lot to Konrad for the insightful presentation.
It was a pleasure.
Okay, so now